There is an idea so deeply embedded in modern agriculture that most people no longer recognize it as an assumption. It is treated as a fact, repeated so often that questioning it feels almost irresponsible. This idea appears in conferences, technical manuals, marketing campaigns, and casual conversations between farmers who genuinely want to do the right thing. The idea is simple: more technology, more inputs, and bigger systems automatically lead to better outcomes. For a long time, this belief seemed reasonable. Agriculture needed to scale, labor became scarce, demand increased, mechanization, synthetic fertilizers, chemical protection, and larger machinery delivered visible results. Yields rose, production expanded, the narrative wrote itself. But what rarely gets discussed is that success in one context does not guarantee success forever. Most agricultural myths do not survive because they are entirely wrong. They survive because they worked once, under specific conditions, and then became generalized beyond their limits. Over time, the original context disappears, but the practice remains. The result is a system that continues to intensify without stopping to ask whether intensification is still solving the original problem, or quietly creating new ones. In many regions today, productivity gains have slowed, even as costs continue to rise. Machinery is larger, more complex, and more expensive. Inputs are stronger and applied more frequently. Yet margins are thinner, soils are more fragile, and dependency on external solutions has increased. This creates a strange contradiction. Farms appear more advanced than ever, yet feel more vulnerable. Decisions become harder to reverse. Systems become less flexible. A single bad season can undo years of apparent progress. What makes this situation difficult to confront is that the damage does not appear immediately. Soil degradation does not announce itself with a warning sign. Compaction builds gradually. Biological activity declines quietly. Resilience erodes season by season, masked by short-term yield stability maintained through ever-increasing intervention. From the outside, everything still looks efficient. Fields are uniform, operations are synchronized, machines run with precision, but beneath the surface, the system becomes increasingly dependent on continuous correction. This is where the myth becomes dangerous. The belief that more technology automatically equals better agriculture removes the incentive to observe natural limits. It encourages optimization of outputs without equal attention to system health. It rewards scale and speed, but often ignores long-term structural stability. None of this means technology is the enemy. The problem is not innovation itself, but blind adoption. When tools replace thinking, and efficiency metrics replace understanding, agriculture shifts from management to maintenance. At that point, farmers are no longer steering systems. They are keeping them alive. This shift rarely feels dramatic. It happens slowly, normalized by routine and reinforced by industry messaging. The cost increases are explained away. The soil problems are treated symptomatically. Each new solution promises to fix the side effects of the previous one. And so the cycle continues. The most uncomfortable part is that many of these practices are still taught as best practices. They are not framed as trade-offs, but as progress. Questioning them can feel like rejecting science, even when the data itself suggests caution. In the next part, the focus moves away from ideology and toward evidence. Not opinions, not nostalgia, but measurable changes in soil structure, system resilience, and economic stability that challenge the assumption that more intensity always means better results. Because the real issue is not whether modern agriculture is powerful. It clearly is. The issue is whether it is still sustainable on its current trajectory. To understand why the dominant model of modern agriculture deserves scrutiny, it helps to move away from slogans and look at patterns that repeat across regions, crops, and production systems. These patterns do not appear in a single season. They emerge slowly, often ignored because they do not fit into annual performance reports. One of the first indicators is soil structure. In highly mechanized systems, especially those relying on increasingly heavy equipment, compaction becomes almost unavoidable. The pressure applied to the soil exceeds its ability to recover naturally. Macropores collapse, water infiltration slows, roots encounter resistance earlier and more frequently. At first, the effects seem minor. Crops still emerge, yields remain acceptable, problems are explained away as weather-related or localized anomalies. But over time, the system adapts in a very specific way. It compensates. More fertilizer is applied to overcome reduced root exploration. More irrigation is used to counter slower infiltration. More chemical protection is deployed to manage stress-related disease pressure. Each input masks a symptom rather than addressing the cause. This compensation creates an illusion of control. The system appears stable, but only because it is constantly corrected. When inputs are reduced, performance drops sharply. This is not resilience, it is dependence. Research from multiple long-term field trials shows a consistent trend. Soils under continuous high-intensity management often lose organic matter over time, even when yields remain high. Organic matter is not just a nutrient reservoir. It is the foundation of aggregation, water retention, microbial diversity, and buffering capacity. As organic matter declines, variability increases. Crops respond more strongly to extremes of drought and excess rainfall. Yield becomes less predictable. The system becomes less forgiving of mistakes. Economically, this creates a dangerous feedback loop. To maintain output, producers must invest more capital each season. Machinery upgrades, input packages, precision technologies, and service contracts stack on top of each other. Fixed costs rise faster than revenue potential. This is why many operations today feel profitable on paper but fragile in reality. Cash flow depends on optimal conditions and uninterrupted access to inputs. Any disruption, whether climatic, logistical, or financial, exposes how narrow the margin for error has become. What often goes unmentioned is that this trajectory is not universal. Systems that prioritize soil cover, reduced disturbance, and biological function tend to show different long-term behavior. They may not always produce record yields in ideal years, but they consistently reduce volatility. Lower volatility is rarely celebrated. It does not make for impressive headlines. But from a system perspective, it is one of the most valuable outcomes agriculture can achieve. The resistance to acknowledging these trade-offs is cultural as much as technical. Modern agriculture has been taught to equate progress with intensity. Bigger machines signal success. Higher input rates imply seriousness. Slower, regenerative approaches are sometimes dismissed as unscientific or nostalgic. Yet many of the principles behind them are deeply rooted in soil physics, ecology, and energy efficiency. The disagreement is not about science, but about priorities. When yield becomes the sole metric of success, everything else becomes secondary. Soil becomes a medium to be managed, not a system to be maintained. Complexity is simplified until it fits into spreadsheets and prescriptions. This simplification has limits. Soils are living systems with thresholds. Once crossed, recovery becomes difficult and expensive. Compaction layers persist for years. Biological networks take seasons to rebuild. Organic matter accumulation is slow and easily reversed. The most revealing data does not come from short-term trials, but from decades-long comparisons. These show that systems designed for maximum output often sacrifice stability, while systems designed for stability tend to protect output over time. This does not mean there is a single correct way to farm. It means that every system involves trade-offs, and pretending otherwise is irresponsible. The real danger of the dominant myth is not that it promotes technology. It is that it discourages questioning. When a system is framed as inevitable, alternatives stop being explored. Innovation becomes incremental rather than structural. In the next part, the focus shifts from soil and economics to decision-making itself. How incentives, risk perception, and industry narratives shape what farmers choose to adopt, and why certain practices spread even when their long-term performance is questionable. Because understanding the system is only half the battle. Understanding why we keep reinforcing it is the harder part. At some point, the question stops being purely technical and becomes behavioral. If the limitations of highly intensified systems are increasingly documented, why do the same decisions continue to spread? The answer is not ignorance. Most producers today are better informed than ever. The issue lies in how decisions are framed, rewarded, and protected from scrutiny. Modern agricultural decision-making operates inside a dense network of incentives. These incentives are rarely aligned with long-term system health. They are aligned with short-term performance, predictability, and risk avoidance. Yield is visible. Soil resilience is not. One is measured every season. The other reveals itself only after years of neglect. When a farmer adopts a practice that maximizes yield in the short term, the feedback is immediate and positive. Advisors approve, neighbors notice, financial institutions feel reassured. The system reinforces itself. Deviating from that norm introduces uncertainty, even if the long-term logic is sound. Risk in agriculture is not theoretical. A single poor season can threaten an entire operation. This reality pushes decision-makers toward solutions that appear reliable, even if they quietly increase dependency. A known system with known problems feels safer than an unfamiliar one with uncertain outcomes. Industry messaging amplifies this effect. Technologies are rarely marketed as trade-offs. They are presented as upgrades, improvements, solutions. Each new product promises efficiency, precision, and control. Rarely do they address the cumulative complexity that results from stacking solutions on top of each other. Over time, the language of agriculture shifts. Farms are no longer described as ecosystems, but as production units. Soil becomes a substrate, biology becomes a variable, success becomes optimization rather than balance. This language matters because it shapes what feels reasonable. When agriculture is framed as an industrial process, industrial solutions become the default. Mechanical force replaces biological function. Chemical correction replaces systemic understanding. This does not happen because farmers are careless. It happens because the system rewards speed and scale. Time spent observing soil structure or biological activity does not translate directly into immediate revenue. Time spent optimizing logistics does. Education plays a role as well. Many training programs focus on tools rather than principles. Students learn how to apply inputs correctly, but not always why the system requires those inputs in the first place. As a result, management becomes reactive rather than preventive. Once a farm crosses a certain threshold of intensity, reversal becomes difficult. Equipment investments lock in specific practices. Contractual obligations restrict flexibility. Knowledge becomes specialized around maintaining the existing system rather than questioning it. This creates a form of path dependence. Each decision narrows future options. What began as a rational choice under certain conditions turns into a structural commitment. Social pressure reinforces this dynamic. Farming is a visible activity. Fields are public. Practices are judged visually. Uniformity is often mistaken for competence. Diverging from conventional appearance can invite criticism, even when outcomes are comparable or better. In this environment, innovation that challenges the dominant model spreads slowly. Not because it lacks merit, but because it lacks protection. Early adopters absorb more risk. Failures are more visible than successes. The cost of being wrong feels higher. Ironically, the same system that celebrates innovation often resists fundamental change. Incremental improvements are welcomed, structural redesigns are questioned. It is easier to add a new layer than to remove an old one. This explains why many farms continue to intensify even as returns diminish. The system does not collapse dramatically. It tightens, margins shrink, stress increases, flexibility disappears, but operations continue, held together by constant intervention. Understanding this dynamic is essential. The issue is not individual decisions, but the environment in which those decisions are made. Change requires more than better tools. It requires different incentives, different metrics, and different definitions of success. In the next part, the focus turns to what alternative systems actually do differently. Not as ideals or philosophies, but as functional designs. How they manage risk, maintain productivity, and rebuild resilience without relying on perpetual escalation. Because critique without contrast is just noise. When alternative agricultural systems are discussed, they are often framed as ideological opposites to modern farming. This framing is misleading and unhelpful. In practice, the most effective alternatives are not reactions against technology, but redesigns of how technology is used within biological limits. What distinguishes these systems is not a rejection of tools, but a different sequence of priorities. Instead of asking how to maximize output first, they ask how to stabilize the system. Productivity becomes a result of resilience, not the other way around. One of the most consistent differences is soil disturbance. Reduced tillage or no-till systems limit physical disruption, preserving soil structure and biological networks. This allows aggregation to form and persist, improving water infiltration and root access over time. The benefit is not always visible in the first seasons, but it compounds. Soil cover is another critical element. Keeping the soil protected with residues or cover crops moderates temperature extremes, reduces erosion, and feeds microbial communities. This constant input of organic material supports nutrient cycling in ways synthetic inputs alone cannot replicate. Diversity plays a central role as well. Crop rotations, intercropping, and varied root architectures reduce disease pressure and nutrient imbalances. They also distribute risk. When conditions favor one crop less, another may perform better, stabilizing overall output. These practices shift the system's energy balance. Less energy is spent correcting problems, and more is invested in maintaining function. Over time, This reduces the need for emergency interventions. Input efficiency improves, not because inputs disappear, but because they work within a healthier system. From an economic perspective, these systems often trade peak yield for consistency. The highest yields in ideal conditions may be lower, but the lowest yields in poor conditions tend to be higher. Variability decreases, planning becomes easier, financial stress is reduced. This trade-off is frequently misunderstood. Agriculture has been trained to chase records rather than reliability, yet long-term profitability depends more on avoiding catastrophic losses than on achieving occasional highs. Importantly, these systems are not static. They rely heavily on observation and adaptive management. Decisions are adjusted based on soil response, weather patterns, and biological indicators rather than fixed prescriptions. This requires skill and attention, but it also restores agency to the producer. Technology still plays a role, but it is applied selectively. Precision tools are used to understand variability, not to override it. Machinery is sized to the system, not the other way around. Inputs are applied where they add value, not as blanket insurance. This approach does not eliminate risk. No agricultural system can, but it changes the nature of risk. Instead of being concentrated in a few critical points, risk is distributed across biological processes that buffer shocks. Transitioning to such systems is not without challenges. There are learning curves. Short-term setbacks are possible. Existing infrastructure may not be perfectly suited. This is why partial adoption often fails. Mixing incompatible practices can undermine benefits. Successful transitions tend to be intentional and gradual, guided by clear principles rather than rigid rules. The goal is not to copy another farm, but to design a system that fits local conditions and constraints. The most important outcome of these systems is not a specific technique, but a shift in mindset. Farming becomes an act of management rather than control. Complexity is embraced rather than suppressed. In the final part, the focus moves beyond techniques and into trajectory. What happens if agriculture continues to intensify along its current path, and what changes if resilience becomes the dominant goal? Because the future of agriculture will not be decided by a single practice, but by the direction the system chooses to follow. The future of agriculture will not hinge on a sudden breakthrough or a universal solution. It will be shaped by countless small decisions, repeated across millions of hectares, guided by the assumptions we choose to accept or challenge. Trajectories matter more than intentions. If the current path of intensification continues without reconsideration, the system will likely become increasingly brittle. Production may remain high, but only under increasingly narrow conditions. Input dependency will deepen, flexibility will decline, the cost of adaptation will rise. This does not necessarily lead to collapse. Systems rarely fail all at once. More often, they become expensive to maintain and unforgiving to manage. Farms persist, but with higher stress, thinner margins, and fewer options when conditions shift. The risk is not that modern agriculture stops working. The risk is that it works only when everything goes right. Climate variability, market volatility, and input supply disruptions expose this fragility. When systems rely on continuous correction, any interruption becomes a threat. Resilience, once lost, cannot be purchased quickly. Alternatively, a shift toward resilience as a primary goal changes how progress is defined. Success becomes the ability to absorb shocks, adapt to variability, and maintain function over time. Productivity remains important, but it is no longer isolated from system health. This shift does not require abandoning technology. It requires rethinking its role. Tools become supports rather than crutches. Data informs decisions rather than justifying prescriptions. Innovation focuses on simplification rather than escalation. Importantly, this transition is not about ideology or purity. It is about alignment. Systems that work with biological processes tend to require fewer interventions to remain stable. This alignment reduces both environmental pressure and economic exposure. The most powerful change is often invisible. Improved soil structure, more consistent water infiltration, gradual increases in organic matter. These do not make headlines, but they alter the system's behavior fundamentally. For decision-makers, the challenge is cultural as much as technical. Metrics must expand beyond yield. Time horizons must extend beyond single seasons. Success must be defined in ways that acknowledge uncertainty rather than deny it. The dominant myth of modern agriculture promises control. In reality, control is always partial. The question is not whether uncertainty can be eliminated, but how it is managed. Systems built on constant correction are efficient until they are not. Systems built on resilience are forgiving, adaptable, and durable. Agriculture has always been an exercise in working with forces larger than any individual decision. Weather, biology, and time cannot be fully controlled. They can only be respected or ignored. The path forward is not about choosing sides, but about choosing direction. Continuing to intensify without questioning assumptions leads to greater dependency. Designing systems that prioritize stability opens space for adaptation. The future will reward those who recognize that true efficiency is not measured by how much can be extracted in ideal conditions, but by how much can be sustained when conditions are far from ideal. In that sense, the most modern form of agriculture may not be the one that looks the most advanced, but the one that remains functional when everything else is tested. And that is a question no myth can answer for us.